Hey, welcome everyone to our final review sessions where we're going to be going over data structures. So for today's agenda, we're going to go over arrays, lists, Vsts, and then we're going to jump into B trees or left-leaning red-black trees, heaps, sets, and maps. All right, so let's take this away with arrays. All right, so arrays are our most basic data structure. Some people consider it primitive, but it actually is technically a Java object. It implements the Java object interface. So I guess that's just a small thing to keep in mind, but it is the most basic data structure and it is native to Java. So a few characteristics, the important ones. One is that once you have instantialized an array, the size or the length, and also the type of that array is fixed. Additionally, we use square brackets to indicate that it is actually an array. So here we have a few examples of how we instantiate arrays. We have an example that uses the keyword new and then string, and within the brackets, we have 5, which creates an array of length 5. In this case, it does not put any values in it. And the note down here just specifies that if no values are specified, then they're initialized to a 0 value. In the case of integers or floating points, a 0 value is a literal 0. However, when we're talking about like characters, strings, or Boolean values, that is equivalent to a null character or false for Boolean. So there's 2 other ways to instantiate an array. You have the shorthand case, which we have an integer array of length 3 with the values 3, 10, and 7. And then we can also forego this, the keyword new, and then this type along with the brackets using simply just curly brackets and the values that we want in our array. Cool, that should be about it. Next up, since arrays obviously have the issue of having a fixed size, lists is sort of like a natural evolution of arrays. And so these are the key methods that I think should keep in mind of the list interface. We have an add method, we have a get method, we have remove, contains, and also a size. These are just the important ones again, just to keep in mind. So the nice thing about lists is that we don't need to worry about sizing because the underlying implementation of our list will take care of any resizes or anything of that manner. The only thing that we really need to care about, which is the lovely part about computer science, is the idea of abstraction, where we only really care about these methods as opposed to how they work. So yeah, they have various different pros and cons, the different implementations, linked list and array list, which we'll go over in a bit. And we know here that unlike arrays, lists are true objects. And in the case, true objects should be put in like air quotes because arrays, again, are Java objects, but you can kind of consider them a primitive. All right, so we have a quick comparison of arrays and lists. Arrays fixed during instantiation, which we mentioned earlier. We use a bracket notation to access them, and they're because we consider them primitive, they don't need to be imported, and you don't need to implement anything in order to use this structure. And it's nice and simple, relatively simple. So opposite to arrays, lists, dynamic size, super nice, don't need to worry about that. You have to import it. It is not native to Java. There's a set of given methods that we saw in the list interface a little earlier. And the implementation can be a little bit more convoluted or complex. But oftentimes when we're using it, we don't really need to care about the underlying implementation. Yeah, so here we just have sort of a comparison of different important things or things that you'll be using often with arrays and lists. So for arrays, in order to get the length, we use .length to get like its class variable, as opposed to lists where we use .size with parentheses indicating that it is a method. When we add elements, arrays, we use square bracket indicating the index, as opposed to list where we use the add method. Similarly, to get something, square brackets again. However, for list, we use .get. And then there's a difference between removal. Arrays, you can't remove anything. Remember that once you have instantiated the array, it will remain that length forever until it gets garbage collected, or your program ends and it goes away magically. However, for lists, you do have a remove function. And basically what this does is that it will remove the index at I, and then it will shift everything to the right of I left by 1, which is the equivalent of subtracting 1 from all their indices. So that's just some like key differences. Let's see. Does add I element shift all the elements to this side or replace elements at that index? It should replace the element at that index. All right, cool. So let's take a quick look at some implementations of lists that we have seen in this class. Excuse me. So first up, we have linked lists. And there's a variety of different ways that they have been implemented in this class so far. We have our int list, which is our most basic structure, where we have a value that we have a variable that contains the or holds the value, and then we also have a pointer to the rest of the list. So in this case, if we look at our diagram here, we have our value here, then we have a pointer to the next one. Again, same structure, we have value and pointer to the next one. And it's a pretty clean recursive structure. However, when we actually implement it and want to use it for its data structure purposes, it can get pretty messy. So I guess the next evolution of this would be singly linked lists, where it's built on a very similar idea of int lists, where except for the fact that we now have sort of a wrapper class around it, where we change the int list class, the idea of the int list, and basically call it a node. And inside the node, you have, the value that we care about, and also a pointer to the next node. And then our sort of wrapper class or a singly linked list class will have a pointer to the first node, and also a variable that contains size. So again, we see a very similar structure as int list, except our little extra box right here. Oh, okay. Avi sorry, that's my bad. Avi made a clarification question that add I, comma element, what I mentioned earlier, right here, does in fact shift all the elements over. That's my bad. Okay, cool. So next up, with singly linked list, we have the issue of it's like, hey, like what if we want to access the element at the very end of the list? Do we have to iterate through the entire thing? So that's where we sort of go to our doubly linked list. And so this is sort of where sentinel nodes come into play. So sentinel nodes are quote unquote secret nodes that are invisible to the outside user. So basically in our implementation, when we do use a doubly linked list or anything with a sentinel node, the user should never be able to know that there is a sentinel node. And we'll see in a bit why sentinel nodes are sort of important in our doubly linked list. So basically, in order to solve the issue that we had earlier where we're like, hey, how do we get the last element in the node? Or, if we're in the middle of the list, can we go backwards? So in this case, we add a extra field to our node class, a prev pointer or previous pointer, which should point to the previous node. And in this case, we introduce our sentinel node simply just to make our algorithms a lot cleaner. It makes adding to the front and also to the back a lot cleaner, and instead of having to write specific cases for our code, we can sort of generalize it. Okay, cool. Any questions so far? Nope, cool. All right, so let's go ahead and do some practice. Here, given a linked list, given a node right here, write a method that basically prints out the reversed values. And I will give you guys sort of a skeleton. There's many different ways to implement this, but this is just one of the ways. So I'll give you guys about like maybe a minute or so, and then I'm gonna have you guys sort of answer in the chat as to what you guys think parts A and B and C will be. Okay, hopefully that was enough time, maybe not. But does anyone have any thoughts for what might go into A right here? Yep, so there's, yep, Jeremy got it spot on. In this case, A should be if n, or yeah, if n is not equal to null works as well. Or not quite, not specifically for this implementation, but really close. So in our case, for A should be if n.next is not equal to null, which Justin got correct. And so if A, or excuse me, if n.next is not equal to null, that means that we go into our conditionals, or we go into the if statement here. So what should B be? What should B be? If anyone has any thoughts, please go ahead and put it in the chat. First dot next. Whoa, okay, yes, yes. Ding, 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 bingo. Reverse dot next, or n dot next. That is our recursive call. And finally, what would C be? Remember, we are trying to print out the values in this linked list. S out n dot value. Yay! Congrats. All right. Yeah, that is our solution. Nice and simple for you guys to look at later if you choose to do so. All right, we just took a quick look at linked lists. Now we're going to take a look at array lists. So array lists are similar to linked lists. However, the underlying structure instead of a linked structure is actually using an array. And because we have to use an array, this data has to be resized. As we mentioned earlier, once you instantiate an array, it is of a fixed length. Amazing thing is that this allows you to index into the array, constant time. And yeah, the key thing is that we need to resize. And generally when we reach the, once we, oh, I think someone's
Yours is 5277.
Let me just mute him. There we go. Fixed. Yeah, so once the array is filled up, we have to basically resize, make the array bigger. Generally, 2 times is a good resizing factor. So let's take a quick look at our resize. In the case, this is our array, or output array, that we're going to resize to. So we take our size, multiply it by our resizing factor, which is 2, come up with all zeros because anything that is not filled, or when we instantialize that does not have an initial value, is 0. We then copy the old values over, which is all this lovely stuff. And finally, we add the element that we wanted to add, which is 5. So one of the important methods to use is system.array_copy, which is basically what is being accomplished at these 2 steps, where we're copying the old value into the new array. So for practice, I'm going to have you guys write your own implementation of array copy. So a few notes. Notice how object here is, or excuse me, source array is an object and not an object array. And yeah, that should be like the only note. Again, we'll have a skeleton for you right here. Why don't you guys take another minute or 2 just to jot down what you think A, B, and C is, and I'm going to ask you to put it in the chat later. All right. I do apologize if that is not enough time, but for the sake of time, we will move on. So what do y'all think A is, or in this case, A and B, because they're kind of similar? Thoughts, comments, questions? Source array, source array, source array. So in the chat, we have source array, which is close, very close. We have Noah saying, yes, Noah says that we need to cast the object array to source array. Right, so the key thing here is to notice that source array is passed in with the type object. However, since we know that source array is an array, we have to go ahead and cast it as an array. So, hello, this works. There we go. So A, we cast the object array to source array, and likewise, we do it for the destination array. What about for C? What should our condition for our for statement be? Yes, perfect. Int I source, or source position. Not quite, not quite. So in the chat we have int I equal to source position, and then I less than blank, I plus plus. So if we start at source position, we can have the issue of if source position is greater than length, which will never go into the for statement. Yes, length plus source position can work. There's another question. Noah asked why source array and destination array aren't of type object array to begin with. Yeah, that's a great question. If you guys know the original developers for Java, that would be great if you can ask them. But I took this directly off of the Java documentation, and they have it as object as opposed to object array. Yeah, so for C, our condition in the case, for this case, is I is equal to 0, I is less than length. What we have in the chat works as well. What about for D? What would we need to do? How would we copy over old values to new values? Thoughts, comments, questions, concerns? Okay, how about? Oh, okay, so shoot, okay, cool, beautiful, lovely. Yeah, so basically in order to copy over the values, we have to get our position for destination, right? And that is starting with our destination position indicated or passed in by the user. And also, we also have to start at our source position, also passed in by the user. And our I is just our incremental value. I think there's a question in the chat. Let me see if I can find it. How would Java know if, where'd it go? How would Java know if an array is an array object? Isn't that the reason? I'm not too sure what that reference is, but let's see. Roy also commented that primitive arrays do not extend object arrays, but they do extend object. So that is why they use object. Yeah, so Daniel, if that doesn't make any sense, could you comment or to clarify your question? But besides that, we're just going to move on. Yeah, this is our solution and validity. Cool. So pros and cons of linked lists. Pros, obviously, we can quickly add elements to the beginning and also to the end. It's also space efficient. You know, if we don't have anything that we care to add to the list, then we're not wasting space because we don't create empty nodes. And also we don't need to resize. The cons are that it's very slow. If you want to get something in the middle of the list, we have to increment either from the front or from the rear of the list. And also, small note, it's like because nodes are its independent class, independent data structure, they will take up more space as opposed to primitives. And array list pros and cons are sort of literally just a flip of linked list. Array list indexing is very fast because indexing into array is just fast. And also it takes up less space because we don't have node classes. Cons, resizing, pain in the butt. You know, it can be significantly slower because you have to resize for specific calls. Yeah, cool. Any questions thus far? No? Okay, cool. So what should we use? Generally, linked lists are good when we are adding or removing values that are at the beginning or the end, or accessing values close to the beginning or the end. And also, or yeah, so one example would be a list of applicants that submit applications for a job. In this case, you can sort of ignore the alphabetical list, basically because the assumption is you have like a queue, right? Applicants are added to the back of the list, and then when the recruiter comes and looks at their applications, they take it from the front of the list. And because adding and removing from linked list at the very beginning and the end is nice, and also it doesn't take up significant space because the node structure is like not a bad reason to go with the linked list. Array lists, because we can index into it, a good example would be a library catalog where we have to index into the middle of the list a lot. All right, next up, leaving lists behind, we're going to take a look at binary search trees, BSTs. So, So one of the properties of Vsts is that every node is the root of a smaller subtree with 2 children. So that's a little mouthful. So we're going to take a quick look at the diagram right here. In this case, 6 is the root, and it has 2 subtrees of 2, 3, 4, and 7, 8, 9. And also, each subtree is sort of its own tree. In this case, 3 is its root with a subtree of 2 and 4, and same thing with 8, 7, and 9. So next up, the left children of each root should always be less than the parent node. So one of the things for BSD in this class is that we don't care if values are equal, or we do not allow values that are equal to be in a BSD. And then again, likewise, for values that are greater than the root or the parent, they always go on to the right side or the right subtree. Cool. And then we have two different BSDs. Here we have a bushy one, because I guess it looks like a bush. I don't know. And then we have a spindly one. And the key thing is that when a tree gets spindly, things slow down. You know, people are unhappy simply because should you ever need to add anything to the end, you've got to iterate through the entire thing. So just quick notes are fine here for a bushy tree is log n, and excuse me, for the spindly one is simply n. We'll have a slide with all the runtimes at the very end, so I would encourage you guys to sort of put that into your cheat sheet. Yeah, and just quick note, time complexity to find a node is generally big O of height. So for BSDs, there's two things that we care about, or the insertions, or excuse me, there's a lot of things that we care about with BSDs, but two important things is insertions and deletions. Insertions should be relatively simple. You take your value and you basically iterate through your tree until you find the next open space. So in this case, we have 5, and we start at the very top. We start at the root of the entire tree, and we ask, hey, is 5 less than 6? Yes, so we go to the left subtree. Then we go to 3. Hey, is 5 greater than 3? Yes, 5 is indeed greater than 3. So we move down to the right subtree because 5 is greater than 3. And then we ask, hey, is a 5 less than 4? No, it's greater than 4. So in this case, we would go down to the right subtree of 4. But since 4 doesn't have any children to its right, we would add it. We would put 5 as 4 subtree. Yeah, so insertion hopefully was pretty simple. Deletion is the more complicated cases. I would personally probably jot down sort of the procedures of deletion in your cheat sheet if you haven't already. So there's 3 cases. In the case that a node has 0 children, or it's a leaf at the very bottom of the tree, then deleting it is pretty simple. You just delete it, you get rid of it, you cut it off. Axe, done, okay. In the case that there is 1 children, it's also relatively simple. So in the case that we want to delete 2 here, the logical place for 0 to go is right where 2 was, and that still maintains our BST property. Because remember, everything that is to the left of 3 is less than 3. So thus 0 is less than 3. And we get our beautiful tree. In the 2 children's case, this is where it gets a little bit more complicated. We basically want to replace a node that we delete with either the largest descendant of the left subtree or the smallest descendant on the right subtree. So the way that I would look at it is that the largest descendant on the left subtree is the value that is the rightmost on the left subtree, which gets a little confusing, but you take a look at the left subtree and you go and find the rightmost element. This case is 4, and vice versa for the right subtree. The smallest element on the right subtree is the leftmost element on the right subtree. In this case, it's 7. So other one should work. So if we remove 5, we can place 4 there, and notice how it still maintains the BST properties. And likewise, should we delete 5 and replace it with 7, it still maintains the BST properties. All right. And this is just a list of BST runtimes. Again, I would probably come back to the slides later and just jot these down. Cool. Do we have any questions on BSTs? Nope. All right. Beautiful. Cool. So we're going to take a quick look at tree traversals, which is sort of like part of BST, I guess, or more so part of trees than anything. So there's BFS and there's also DFS. So in the case of BFS, it stands for breadth first search, which means that we will visit the nodes level by level. And thus, basically, the key thing that I would jot down for BFS is that the underlying implementation uses a queue. And how this works is that we'll start at A, and then we'll put all its children onto the queue. Generally, we go alphabetically, so like B, then C, and then we pop off from the queue, pop off from the queue, then you go to B, but because B has nobody, no children, very sad, we don't add anything to the queue. Then we go to C, we look at children, we add D, E, we visit D, no children, E, no children, and we're done. And yeah, this is what we have. Cool, and then we have DFS, depth first search, and there's 3 sub searches. There's pre-order, in-order, post-order, and the key thing is that instead of a queue, we use a stack. And remember, a queue is first in, first out. A stack is first in, last out. So again, I would probably, if you haven't already, probably just write pseudocode of pre-order, in-order, and post-order onto your cheat sheet. I think the recursive method is probably the cleanest one, or cleaner than iterative. I don't know, I just like it better. Okay, so when we're looking at pre-order, especially when we're doing it on paper, the way that I approach it is I would draw a line that sort of goes through all of the elements. And whenever I reach the 9 o'clock position, I would write that down. And I would consider that as we have visited that node. 9 o'clock position being right here. So if we were to look at this in practice, we start at the very left and we end up at the very right. We see 9 o'clock position A. Okay, cool. 9 o'clock position of B, B, D, then E. Come up here. We're at 9 of C, 9 of F, 9 of G, and then we end up here. And thus we get our pre-order. Can you repeat what you said about queues and stacks? Yeah, so queues is first in, first out. It's like the line that you have at McDonald's. You know, you wait in line, first in, people that come after you will have to wait in line after you to go to the cash register. Stack is like a stack of papers. You know, when you stack on top, the first things that you take off will be the stuff on top. Okay, cool. So we went over pre-order, now in order. For in order, when I look at it, I jot it down whenever the 6 o'clock position is reached at each node. So again, starting on the left, we go down, oh, we have reached the 6 o'clock position of D. So we drop down, keep going, B, E, A, F, C, G. And that is our in-order traversal. All right, and then we have our last one, our post order. So in this case, we jot it down, we visit the node when we reach the 3 o'clock position. So in this case, we start at the leftmost position at the root, go down, 3 o'clock of D, so we jot it down, 3 o'clock of E, 3 o'clock of B, 3 o'clock of F, 3 o'clock of G, C, A. Should be relatively simple. Let me know if you have any questions on that. So again, we have a quick practice, probably like a minute. Just jot down the pre-order, post-order, in-order traversal of this tree. Okay, hopefully that's enough time. If not, I'm sorry. But yeah, so what do you guys think for pre-order? Pre-order. A, B, E, C, G, A, B, C, blah, blah, blah. Yes, yes, that is correct. A, B, E, C, G. Nice. What about in order? B, E, A, C, G. Yes, beautiful, beautiful. And what about for post? E, B, G, C, A. Yes, that is correct. E, B, C, G, E, B, G, C, A. Dang, my mouth can't work. All right, cool. And yeah, that wraps up my portion. Next, I'm gonna hand it off to, I think Saad.
Yes, that is right. Thank you, Jesse. Let me just share my screen 1 second. All right, you all should be able to see a little B tree thing, right? Is that right, Jesse?
Yes, I can.
Okay, perfect. B trees. So B trees are 2-3 trees. They serve a similar function to binary trees while ensuring the bushy structure. So as you can see, oh, let me just, there we go. As you can see kind of in the middle over here, we have a node that has 2 elements inside as opposed to just 1. And because it has 2 elements, it has 3 children. For example, the numbers 1 and 2 are less than both 3 and 7. 4 and 6 are between 3 and 7. And then 9 is greater than 7. All leaves are the same distance from the root. And the point is that the max height of our tree is always log n. So in terms of inserting into a B tree, the steps are pretty simple. First, you insert into a leaf node. If the leaf node is full, so what does full mean? Full means there's, let's say, 3 or more numbers. You push the middle element to the parent node, and you keep repeating so long as that's necessary. If the root node is full, then you push the middle element to make a new root. So this is a really good example where we insert 5 into that 4-6 node, and you see that we get a node that has 3 elements right over here. So we push 5 up 1 level, and then we have another node with 3 elements, and we repeat 1 last time until everything is fine. Okay, deletion. Deletion also for a B tree kind of reminds me of a heap. So you kind of have to swap the value of the successor with an argument to delete. And then you can safely remove the argument to delete. So what does that mean? If you want to remove 17, for example, I'm sorry, it's not similar to a heap. It's similar to a binary search tree. So what's the successor element to 17? Well, that would be 18, right? In this tree, that's the element that is exactly next. How do you kind of figure that out? Well, you kind of keep alternating between right and left, right? So you know that the next element is going to be a little bit bigger than 17. So we definitely need to go right. And then if we can go left, that's beneficial. But since 18 is the successor, we swap 18 and 17, and then we safely remove. And this is just something to notice. When you do this, the successor will always be a leaf node. That's why it's safe to remove. Okay, that's B trees. Nothing too crazy there. Red-black trees. Red-black trees, on the other hand, are binary search trees that retain that same property from B trees, in that a red-black tree and a 2-3 tree, a B tree, will always have a one-to-one correspondence. That's the most important thing to remember. So what you should know about red-black trees is that black edges are the equivalent of a normal edge in the corresponding 2-3 tree, and red edges are the equivalent of the implicit connections between values in the same node in the 2-3 tree. That was a bit wordy. What does that mean? Well, you can kind of think about a red-black tree as the same as a 2-3 tree, except that any node that in a 2-3 tree has 2 elements is now split up into 2 nodes. The only difference being is the edge between them is now labeled a red edge. So let's go look at some more rules. So first, every edge is either red or black. No node can have 2 red edges, and right edges cannot be red. Okay, so the colors are a little bit difficult to see. I'm also red-green deficient, so we'll try to make it very clear on the exam. But this tree over here, it has 2 edges. Its left child and its right child are red. So this is an invalid tree. This one is both black. I think this should be fine. And then this one on the right-hand side, this is a right edge, which is red. That's not allowed. Okay, this is the really important property. This slide, everyone should just commit to memory. How do we convert between 2-3s and left-leaning red-black trees? Well, see how this node right over here is a 3-7 node. We see the exact correspondence is, hey, can you disable, someone is drawing on the screen. I'm just gonna clear, okay, clear all drawing. Yeah, all right, sorry, back to that, sorry for the interruption. Where was I? Yes, we have a 3-7 node, and we have, which is right over here, and we have 3-7 right over here. The point that you need to understand is that because it's left leaning, we'll take the left element and kind of push him down, and whatever edge is between these 2 nodes is now labeled as red. Okay, you see a very similar concept with 2 and 1. 2 and 1 is also 1 node in the 2-3 tree. All right, so that's the one-to-one correspondence idea. Now let's talk about balancing operations. Okay, so what's the point with the left-leaning red-black tree? We want to make sure we have a bushy tree, right? So we have these rules that say if ever, one of our properties, i.e. Maybe the right edge is red, or we have 2 left edges in a row, or we have a node that has 2 children who are both red. Whenever these properties exist, something has gone wrong. So we take balancing operations to correct that. Lucky for us, there's only 3 balancing operations, and they're pretty straightforward. So first is rotate left. What I like to think of rotate left is you take the node it's being called on, you take its right child, you push it up. So I'm just going to annotate that very quickly. You'll see that the right child of A is B. We kind of pushed B and A into the same node. That's a little bit how I like to think about it in my head, kind of like an intermediary step right over here. And then we pushed A to the left. And you'll see that right over here, A has been pushed to the left. Very similar idea with rotate right. With rotate right, we see that A, we take his left child, put that into a node, A, B, and then we'll push A to the right-hand side. The last thing that you have to ask is, what do you do when you have 2 nodes that, are your children that are both red edges? Well, this is called a color flip. So you'll see that both of these red edges became black and the parent became red. All right, moving on. Llrb insertion. So insertion is very similar to a binary search tree with the following checks. The color of the link that you add in is always red. Now, the last 3 steps is just ensuring the left-leaning red-black tree property. So if you insert it on the right, you want to make sure you rotate left. If you have double reds on the left, you need to rotate right. And if the left and the right child are both red, you just flip the colors. These rules I'd recommend you just memorize. And if you want an intuitive understanding, you always just go back to understanding that, oh, there's a 1-to-1 correspondence with a 2-3 tree. So I'm going to look at some examples. Let's say we have this tree ABE and we try inserting S. So we'll see that S you always add with a red link. That's just a rule. Always add with a red link. And because you're not allowed to have a right red edge, you rotate left. Okay. Now let's say we try adding Z, right? Same idea. Z gets added to the right-hand side and it gets added with a red edge. Now we need to flip the colors because S has 2 red children. And now we have another issue, which is that B has a right red edge. So then we rotate left. All right. This is very similar to before. LLRBs in a 2-3 tree have a 1-to-1 correspondence. If you want to insert 18, let's say, so just comparing, in the left-leaning red-black tree, 18 shows up right here, and in the 2-3 tree, it's in that 2-3 node. If you want to insert 38, it kind of follows from there. Okay, so just a quick summary. Balancing operations are necessary under the following conditions. If both the branches are red, if a right-leaning branch is present, or if there are 2 left-leaning branches in a row. So this is how you ensure that the left-leaning red-black tree is valid. Okay, here's a really helpful table that kind of just goes over these 3 data structures and the runtimes for insertion, deletion, search, and height. As you can tell, for a binary search tree, it's technically possible that you have O of n height, right? That's kind of like a linked list. Imagine, if you will, you added the number 1, and then you add the number 2, then you added 3, 4, 5, 6. Because they're consecutive, you'll keep spamming add to the right, and you'll basically end up with this, linked list type structure. On the other hand, for B trees and LRBs, we ensure there's only log n height through our color flipping operations. Okay, we're a bit short on time, but I think we can just think about this practice problem, which is consider the following left-leaning red-black DST. Problem number 1 is really interesting. Which one or more of the keys below could be in the node labeled with the question mark? So if you could drop your answers in the chat. Yeah, the answers in the chat are totally valid. So what's the general idea here? We know that this question mark has to be greater than G, because it's to the right-hand side of G, and it has to be less than L. So then ask yourself, what are all the letters that are greater than G and less than L? H, I, J, K. Okay, perfect. Question number 2, what is the color of the link from the node labeled with a question mark to its parent? Is it red, black, or can it be either? Yes, so what you all are saying in the chat is totally correct. This is, in fact, a red edge. You would see that if you were to actually insert this question mark in a 2-3, for example, there would be question mark and L would be in one node together. Therefore, it has to be a red node. Okay, the last question takes a little bit of sketching to do, so we'll skip that. But of course, you all can look at the slides yourself, and you end up with this tree if you add the key U. So you can see it got shifted, moved around quite a bit. Okay, another conceptual question, which I think we'll have time for. So for each of the situations below in a valid LLRB tree, list whether the node is red, black, or either. Recall that a node's color is the link connecting it to its parent. So let's start off with the first one. What's the largest key in a tree with more than one node? Largest key in a tree. Let's think about that. So let's say I have, I don't know. Oh, I shouldn't draw in red. That's confusing. Black. There we go. Let's say I have the number 2, and then I'll just label R for red. I've got 1 over here, and then I'll have, let's say 3, right? So what do we know about the largest key? You just keep spamming right. Therefore, it has to be black, right? Because it's impossible that you can have a right red edge. Therefore, it must be black. Okay, let's go to this question over here. A node whose parent is red. Definitely black, right? We can't have 2 consecutive red nodes. Okay, the smallest key in a tree with more than 1 node. That's right. This one is, in fact, either. So let's see. This example that I've drawn on the board or on the slide, this is an example where it's red. And then obviously, if I just drew, let's say 1, right? This is technically a black edge because the root is technically black. Okay. A node whose children are the same color. Yeah, it's also either. A node with 2 children the same color can either be red or black. Okay, so that should conclude left-leaning red-black trees. Now we're on to, all right, just quick question from the chat. So wouldn't it have to be red for this last one? No, not necessarily. Here's why. Let's say I have 2 over here, or let's use a different number. Let's just use 5. We've got 5 over here. We'll go down here. This is a red edge, and we've got, let's say, 3, right? It is possible. Well, first of all, we know that if your children are the same color, it must be the case that they're both black edges, right? You cannot have a node that has both red edges as its children, right? So we know that this is black, but the question is not asking, oh, what are the color of the children? It's saying this node, what is its color? Well, it can either be red, as in this example, but it can also be, for example, let's say 3, 5, or I'll just draw on the side. So right over here, if I have a right edge, we know that this is black, right? So this is 6. It is technically possible for both of its children to be the same color, and you can see it's a black edge. So it can be either red or black. Okay. So that was answer to Preethi's question. How does a 3-node 2-3 tree have a black smallest child? How does it? Let's think about that. Let's say I have 1. I don't think it's 2-node 2-3 tree has a red smallest child. Jesse, I think you might be just a little bit confused. So a 2-node 2-3 tree has a red smallest child, but a 3-node 2-3 tree has a black smallest child. Okay. Any other last questions on left-leaning red-black trees? If it helps, I can draw this example out. So a 2-node 2-3 tree, what does that look like? Well, if it's 2 nodes, we know the 2-3 representation is just like this. So the representation of left-leaning red-black tree is like 1 and 2 with a red edge between them. Okay, 3-node 2-3 tree. So this can be like 1, and I don't know, let's just say its right child is 2, 3. Valid. I think this might be valid. Okay. Oh, sure. Yeah, 3 nodes to the left. Okay. All right. that should be all for me. I'm going to hand it off to the next section is on hash tables.
Sorry, I'm just going to share my screen.
Yep.
Can you guys see the slides?
Yes, we can.
Okay, I'm going to assume that you can. Cool. So we're going to be going over hash tables first. And the general idea of hash tables is that they allow us to store, look up, and remove items in essentially constant time. It's amortized. And in case you don't remember, the general structure of a hash table is there's a bunch of bins which we put, that we put items into. And the way we do this is we first have a hash code, which maps any object to a specific integer, right? And this part is irrelevant of the hash table, right? You can have any function that just generates an integer based on an object. And we have criteria on what makes a good hash code, but it can literally be anything. I can say like, take the first letter of the string and then map it to a specific integer and say that's the hash code. With the hash code, we then have a reducing function that maps the code to a specific bin in the specific hash table. So for instance, say I had a hash code that just did what I said. It somehow converts the first letter of every string to an integer. And that would give me like 26 integers, but say I only wanted, for some reason, 3 bins, right? I could just divide each integer by 3 to reduce it down to a specific code that maps to my specific hash table. So the reducing function basically takes the hash code, which is general, independent of the hash table, and makes it specific to the hash table. So we can fit all the elements into a finite bin. How do I switch? Why isn't it switching sides? Okay, cool. So the process visualized here, we get the object in and gets hashed using the hash code. And this can be any number. And then our hash table uses the reducing function to convert it to a specific integer that tells us which bucket to put this object into. And then the object gets put into the hash table. Now, there are certain properties that hash functions have to have. Firstly, they need to be deterministic. Basically, if I hash an object twice, both times should return the same hash code no matter what. So every object should have an intrinsic property that determines its hash code. You shouldn't be able to get different hash codes when you hash the same object because that would completely invalidate the purpose of a hash table, right? You'd never be able to look up the same element again. Then if the dot equals if 2 objects are equal using the dot equals method, then we also want the hash codes to be equal. This is consistency. Basically, if it's the exact same object, you want them to be hashed to the same thing, even if they're under different variables. Now notice that the reverse is not always true. You can have the same hash code for 2 elements, but they might be different objects. And this is what causes hash collisions. With really good hash codes, these are exceedingly rare. You know, hash codes that are used in global standards have very few collisions, but this is possible. So this is what makes what makes a hash function good for the purpose of hash tables. So firstly, it needs to be uniformly distributed. We want the hash values to be spread out, because we don't want all the objects to be mapped to the same bucket, because that would defeat the purpose of a hash table. We also want this to be efficient. It shouldn't take forever to compute the hash code. And that's not particularly relevant to you guys, but you just want it to be fast. Okay, now a hash table collision is different than a hash collision. So the hash collision we talked about at the beginning, when 2 objects are not the same, but they hash to the same value. A hash table collision is more common, because a hash table collision means after we've done the reducing function, those values are the same, which means they end up in the same bin. So for instance, 2 objects might have entirely different hash codes. Let's say we go back to that alphabet example. But say we hash them all down to 3 bins, then multiple objects will collide naturally. So that's a hash table collision. And this generally makes the structure that we're using to store values grow. So in this case, it's an externally changed hash table, which means each bucket basically has a linked list, and each element are added to that linked list. And this causes that to grow every time there's a collision. So here there were 3 hash table collisions in bucket 0. There were none in bucket 4, 2 in bucket 8, and 2 in bucket 9. Obviously, it's better for us if there are less hash table collisions because we want objects to be spread out. We would prefer if they're not mapped together. Okay, the load factor is an intrinsic property of a hash table. So the load factor is n divided by m, where n is the items in a hash table and m is the number of buckets. So this is basically the average number of items per bin. And if it's less than a certain constant value, we have amortized access time. And if it exceeds the threshold value, we can just resize the hash table and rehash every element to put them back into bins to get the load factor back down to a manageable level, which is why we always have amortized constant access time. So we do need to choose hash codes that generally distribute well. Otherwise, the load times will constantly get out of control and we'll have too much resizing and it won't be a good thing. So, something that just maps everything, for instance, to the same bucket would basically result in a linked list here as a gigantic chain. And no matter how many times you resize it, it's pretty pointless. Okay, so a general look at the runtimes here. Hash tables without resizing are typically over n because the objects aren't spread out as the externally chains grow. But with resizing, both contains and add operations are generally constant time because we would set a certain load factor limit, and past that we would resize it. So no matter what, checking to see if the hash table contains something or adds something would be constant time because we would just go to the specific bucket with our hash code, and that specific bucket would have a finite size defined by our threshold. Okay, we're gonna do some quick checks to make sure that everybody's comfortable so far. And if there's any questions, please ask them. So let's take a minute to think on these questions and then we'll discuss them together. If two items have the same hash code, will they be in the same bucket? If there are multiple items in the same bucket, how would we retrieve one of them? And suppose you have okay, we'll do the third one separately because that's a bit bigger. So for the first two questions, any ideas? Just drop them in the chat. Sorry, 1 second. I have somehow bricked my computer. Okay, sorry. No, okay, I did not mean to go to the next slides, but that is okay. Chat, I'm doing, right. Okay, yes, and use dot equals. Yeah, Preeti, and okay, generally people got the answer correctly. So if two items have the same hash code, they will be in the same bucket. That is the entire purpose, right? Because even if, no matter what the reducing function is, it will reduce them down to the same thing because the reducing function should be deterministic. So given the same hash code, they will end up in the same bucket. Now, if there are multiple items in the same bucket, how do we retrieve one of them? We would iterate through that external chain and use the dot equals method to find the specific element. So this is, for instance, one of those buckets in the example we looked at before. It has 3 elements in it. Say we were looking for hug, we would iterate through this and find the object that equals to hug. And this is the part that would take time if we didn't amortize it and spread out the elements. So is there a question in chat? No, okay. Oh, I see answers to the third question. We haven't got there yet, guys. But the third question, if since we don't go over it, suppose you have a hash function that assigns word to bins based on the ASCII value of the first letter of the word. Is this a good hash function? Why or why not? Okay, go ahead and take some time to think about that. And drop your answers in the chat. Okay, yeah, I think people are generally getting the right answer. It is not a good idea. And the reason being, firstly, it's not going to be very well distributed because if everything in our list, as the example says, started with letter A, they would all end up in the same bucket. And that's not a good thing, right? And that would, again, take our runtime to O of n instead of constant time. There's also very few ASCII letters, so it's not very scalable because past a certain point, we wouldn't be able to distribute well across the buckets. So past 256 buckets specifically, it wouldn't distribute well. Okay. Yeah. So this is just some discussion on load factors. Why is a high load factor a problem, for instance, 3.8? And how can we fix hash tables with a high load factor? Also, I think somebody might be unmuted in the background because I can hear typing and I'm not typing. Right. So I think people got the first question right. It's with a high load factor, it means we'll have longer external chains, meaning the runtime is longer and it's not really constant time. So this is not a good thing. Fortunately, we can fix this by just adding more buckets to the table and rehashing all the elements to distribute them again. Now, again, this part might be a bit confusing until you remember that there is that function we have to convert hash codes into our buckets, right? So you might think that if we rehash them, we'll just end up with the same thing, even if we add more buckets, but that's not the case because our function that maps hash codes to specific buckets would account for the fact that there are more buckets. So this should resize the entire hash table. Okay, that is the end of the hash section. We're going to moving on to heaps. How do we calculate load factor again? That is, in the previous slides, it's the total number of elements divided by the number of buckets. Okay. I see more questions. Right. And I highly recommend, like, if it's challenging, remember, just note that down in the cheat sheet, right? It's just short formulas. Okay. If there's no more questions, we move on to heaps. So the motivating example behind heaps, before we actually go into the heap structure themselves, is priority queues. So that's an interface which has 4 methods: add, get smallest, remove smallest, and size. Basically, it's some sort of data structure. We can add items to it. On demand, you can get the smallest item. You can also remove the smallest item from the list, and you can get the size of it, which is not that relevant. So we can back this up with multiple data types, including ordered arrays, bushy BSTs, and hash tables. And these have these runtimes, which is your question. Okay. Yeah. So this is the data structure we've seen so far, and they can be used to make priority queues because priority queues are just interfaces, right? So anything can be behind it as long as it implements these 4 methods. These are not, however, the best data structures to back it up. And as the section of this presentation suggests, that is actually heaps. So we're going to go through heaps. And heaps, basically, we're dealing with binary heaps, and they satisfy only 2 properties. 1, they are complete, and 2, they satisfy the min heap or max heap property, depending on the type of heap they are. In this case, we're looking at a min heap. So complete means that it only has missing items at the bottom level as far as possible, meaning all elements go to the left. So this is complete, even though it's not fully bushy, because the only element that's missing is all the way to the right. So this could also be complete if number 3 was missing as well, because that still means all possible elements are as far left as possible. It also satisfies the min heap property, which means every node is less than or equal to both of its children. If it's a max heap, the property is flipped. So 1 here is less than 4 and 2, 4 is less than 8 and 5, and 2 is less than 3. And again, for a max heap, this property will be flipped. These are the only 2 properties needed to satisfy for this to become a heap. Okay. So let's just take a quick look at this and determine which of these are valid max heaps. So before we looked at min heaps, max heaps means the property is flipped, right? All nodes have to be greater than or equal to their children. Okay, so we've got the correct answers in chat. 1 and 4 are valid max heaps. So does anyone want to take a stab at why 2 and 3 are not valid max heaps? Okay, yeah. So they both actually are not max heaps because they both violate a different property of heaps. The first property is completeness, which tree 2 violates because this node 1 should be here. It's not complete filling out the levels, right? So we don't want an element down in this 3rd level unless the tree is completely filled out at the 2nd level. The 3rd heap is not valid because it doesn't satisfy the max heap property. 5 is less than 8. We need it to be greater than 8. Okay. And 4 is also less than 6, so it's invalid for multiple reasons. Cool, let's move forward. So these are the operations that we need to implement on the heap so that it can successfully back up a priority queue. Get smallest, add, and remove smallest. And we've described here the methods on how this works, right? But let's take a look at a visual example for this. So firstly, get smallest is pretty simple. You just return the element at the root node, right? Because of the min heap property, the element all the way at the top has to be the smallest. That actually doesn't require you to do anything to the tree, to the heap. Oh, sorry, I keep saying tree. I mean heap. My bad. Right. Adding means we've used an example of employees of a company here. But yeah, for adding, you put it in that element in the last position and then switch upwards. And we'll see a visual example of this. And remove smallest, you take the element off the top, replace the bottommost node all the way from the bottom right, and then switch down until it's valid. And we'll take some visual examples here, which will make it a lot clearer. Okay, right. So for add, say we want to add 3. It goes all the way to the bottom in the furthest bottom rightmost position. Now, this is not valid because 3 is less than 8, and this is a min heap. So every node needs to be less than or equal to its successors. So we just switch it up with 8. This is still not valid. So we switch it up with 6 because it's less than 6. And now 3 is greater than 2. So we do nothing. And this is now a valid min heap. So to reiterate, we add it all the way to the bottom and then switch up until it's a valid min heap. Do we have a question in the chat? Sorry. Okay, no. Sorry also if I'm not very responsive to chat. It doesn't pop up that easily when I'm screen sharing. Okay, delete minimum. So what we do here is we remove the element from the very top, the number 2, and that's gone, right? That was the smallest. We know that's smallest because it's at the root of the min heap. And then we switch up the furthest rightmost element, 8. Now this is obviously not a valid min heap because this is greater than both 2 and 3. So what we do is we switch it down with the element that's most fit to be above it. So the smaller element, 2 is the smaller element here. If these are both 3, you can break that tie arbitrarily. I think generally we recommend just syncing left for consistency, but they're not equal here. 2 is less, so we just switch this way. And then we switch with 3, and we switch with 5. So it's basically the opposite of add, right? We've taken this element to the top, and we just keep switching down with the smaller element until it is no longer smaller, greater than its children. And in this case, 8 needs to go all the way to the bottom for that to be true. And this is now a valid min heap again. Oh, sorry. Any questions on these 3 operations? I keep clicking and actually no. Okay. So I'll just go over this operation real quick again because it's really important. You take the bottom rightmost element, move it up, and then just sync to with the smallest element. All you have to do is switch it. You don't really have to think that much beyond that. So 2 switches with 8, 3 switches with 8, 5 switches with 8. And this just magically ends up as a min heap. Okay. If there's no questions on that, this is a pretty useful table that just talks about the efficiency of priority queues with heaps specifically. And so add is log n because we're going to add an element at the bottom and then keep switching up, right? Get smallest is the most important one. It's constant time because we just have to read the element at the node, at the topmost node. So this doesn't matter how big the heap is, no matter what, it will just read that element. So it's constant time. And remove smallest is log n because it's basically add, but upside down. Okay, and these are all the other runtimes that we saw earlier. You can see that heaps are, on average, across all operations, the best data type for priority queues because they're log n for 2 operations and constant for get smallest, which is better than all the other options. And any other questions? Because that is the end of the heap section. Okay, if there are no questions, then that is the end of my part of the presentation. Ideally, Anjali would say something here.
Yeah, I think she dropped out because of connectivity issues. We can probably,
Okay.
but I do think maybe we should save the last few minutes just for some general questions.
Mm-hmm. Yeah.
Will we go over searching in the graph section tomorrow? Let me just double check what is going on tomorrow. Yes, and feel free to go if you need to, just since we have ended early. Maybe someone wants to stop the recording since we're done.